class, this is a recorded lectures 32 for Monday class, April 11 to 2016. In this lecture, what my plan is to further elaborate the example of problem 10.2 from the textbook, and I believe that the example will gradually increase the number of elements in a given schematic. That you will see that what are the required update that you will have in order to go through this backward and forward step. And the way how I do it for this scripting manuscript is not is not flexible to any kind of topology. So it's sort of hard-coded in a way so that it will give you the idea about what are the steps you really need to go through. But eventually, what you will have to know is that, just like the last lecture, what I did was I showed you a spanning tree with multiple numbers of nodes, and the way how you go through the backward and forward, how you go through each node of navigation is really in precedence of the higher level of depth level for those nodes that will require getting the information before you proceed to the lower level depth of the nodes. So that's the reason why that when you are dealing with a more complicated topology situation, you want to program in the way that how the computer will do that job for you, because iterative process with a large number of nodes, that's no fun to do it manually in paper. But to appreciate what we have been trying to achieve here for this three-phase unbalanced powerful analysis, particularly for the radio network, this is the way to go, because it will assure convergent result. I think one of the publication by the author of textbook, Bill Kirsting, that was a publication that actually I can maybe send it to you guys. The paper is that they were published in maybe late 80s. Talk about how this backward-forward conversion will actually guarantee conversion, whereas if you do this under the same topology in the Y matrix formation, not only you will inflate the number of memory that you might have, but in terms of managing all this backward-forward, iterative process of computation, sometimes you might have some errors because of some singularity issue. So that actually significantly degrade the quality of the computation result in the end. So those are the things that I always want to look into this specific formulation with the right approach to the problem. So let's see. The homework 6 is actually due on Wednesdays. So as I said before, this is postponed not on Monday but on the Wednesday. So you have about 2 more days, presuming that you are watching this today on Monday, and in a comfortable place at home. So this is Wednesday, April 13. So it will be 1:04 before the Wednesday class that we will meet, and you probably will see that on canvas as well. And this, what I would like you to do, as I said last lecture, is that come prepare of the question for the exam 3. If you want to give me a heads up, send me an email. Send me an email so that I will know what are the questions that I can prepare, so that I can discuss about this during the class. And that way, everyone get benefit, and not just you get folks on campus, but online enrollee. So I know that after the exam 3, we're going to have to deal with a project in the following week. So what I would do, as soon as we have meet on Wednesday, I probably will organize who will present first, who will present next. The following weeks will, Monday, Wednesday, Friday, will be reserved all for presentation. So you can do the math here. 12 minutes presentation, 2 minutes for question. That will be 14 minutes per group. If we have 15-minute class meeting, then we will have about 3 presentations each lecture next week. So that means if we have 10 group, then we probably have to crank in some of the group in one of the 3 days class meetings in order to make sure that we have everyone covered. And I'm going to find out what are the possibilities with the IT to figure out how to do that. And as I said earlier, everyone has the right to evaluate the presentation. So try your best shot to present it in a simple way and clear, so that your classmate would know what exactly you are presenting. Because this is not the kind of simulation of result for the project, but indeed I'm assigning a very specific topic randomly to each of the group, so that everyone will learn something about what is unique about this problem, and then you can present it. And it will also set out a good way how you connect this class of material of distribution engineering 1 to the next class, distribution engineering 2, because we're going to talk a lot more technically for in the fall semester about how to deal with GIS data, how to do the graph modeling, how to do the short circuit analysis, fault location, isolation, restoration, or any kind of outage management, cruise coordination with the power outage, trouble ticket, and so on and so forth. So those are the things that we will go through in specific video. So this is the overview about how we have gone through so far, and unfortunately I do not have a lot of time to cover every single distribution transformer type, but my previous lecture I also asked you guys to actually did that for the shake for of exam 3, because time is valuable, and if you do all the summary or generalized matrix A, B, C, D, and capital A, B for each of the distribution transformer, it's all in the textbook. The author proved everything. You need just to have to find out those information and put it in the table form that you have, so that you can apply those. Or if you choose not to do that, it's your prerogative. I think that this is something I would like to see from the author, but you know, for space purpose, I think he already decided not to do that. That's fine. But for your exam, then that would be very useful to put it. Even for the regulator and the line model, if you can do that, that will save you a lot of time. Because when you do this iterative process of backward and forward sweeping for this unbalanced 3-phase power flow, it will help you to get to the point and apply those matrices instead of flipping the textbook around and waste for 15 minutes and looking for something that you don't even quite sure about, right? And that's the time management I'm talking about for exam. And so today I'm going to talk about 10.2 example for the MATLAB script, and what I would do is make also the M file available to everyone, so that you can download and run it and verify those results. And then if you have any question, you can feel free to actually email me or talk to me at my office, or you can also talk about this for this exam review time, which will be on next Wednesday. Now, back to our business. So the last lecture we talked about 10.1, that was a pretty straightforward 10.1. So they basically have 2 questions for 10.1. One question is to, let me just quickly review it. One question is to find out the generalized matrix, which I think is a pretty straightforward, and then a loop of the script that illustrate the backward forward sweeping between node 2 and node 3. So basically node 2 and node 3 has a load, and how we go through this iterative process, and to show you how you can formulate a problem for modified line model under the constant power circumstances. But even with, as I said before, even with the complex power that you have formulated here, you have to convert those information into current information. So that's the I ABC M equal to conjugate S divided by square root the voltage at node 3. So those are the necessary things, and as you can see that each iteration, when you have the force going back to each iteration, as long as it doesn't converge, it will use the last computed voltage value and you put it right here for the next iteration. Remember when I say that during the initialization stage, which means when at 0 iteration, we don't have the value of voltage, so you can simply use the nominal voltage value and plug it in, and then you do this iterative process. And during the forward step, when you have V is determined, then you can use that voltage and plugging in instead of using the O value. So having this step is very important, because without updating the forward step, you wouldn't have any new voltage of the V3, right? So this is a hard-coded way how you do this iterative process, and the reason I hard-code it to show you that the step necessary required. But if you have a complex topology, let's say 1,000 node here, then you really have to understand how the navigations of those backward and forwards based on the topology of the distribution feeder. So those are the things that may be more complicated, but conceptually this is what you need to know, how to update the voltage and current iteratively. So here I am, here we are, the problem 10.2. This is on the page 354 on second edition, but it's the same 10.2. We are going to include more information about the regulator. So you see that I am highlighting this in the red color. So the very first step for regulator for you to do the dealing with the regulator is to initialize all required for the equivalent Z value to the load center, and those steps, the ratio, PT ratio, N ratio, CT ratio, and the voltage level, what are the bandwidth, right? And then what are the required high and low, the plus minus thing, and then what are the equivalent impedance after you find out the load center and the average. And then the next step you will have to do is to find out the compensator value, the impedance set. So those are the procedural, as I said, it's kind of boring, but this will get you. Computing is about what you need to calculate the impedance information. And then question 3, compute the compensator relay voltage, compute the relay voltage, and then in the end you include more regulator information, generalized matrix for regulator. In this case, looks like it is a typical 3-phase regulator model. So you see that A, B, C, D, capital A and B, and we will need this for this backward forward sweeping next. So I'm guessing is that since we now include additional element, not just the line but also the new regulator value, we are going to include new information for, you see, A, B, and C, A, B, and C. So I'm trying to be systematic here so that you get current for the backward, update the other terminal of the line, and then update another terminal of the regulator. So that's why you have A, B, C, A, B, C. And during a forward step, since you already have this updated, you're going to predict, correct the value of V2 and V3. So this step is actually quite straightforward. As you can tell, this is probably the C part is the new step that we have included, and then as well as the V2 here, because this is probably the regulator. So you can see progressions of adding new element, and then you have to initialize all those specific elements. But for the for loop here, it's actually pretty much the same thing. And then when you get converged, then you're going to find out what's the voltage required for V3 after the regulator kick in the modifications of voltage. That's what you get for in terms of 120 volt base. So that's the load voltage for V3 here. So the rest of it actually is trying to figure out the new value from power flow for the compensator and the voltage relay necessary for this specific regulator. So as you can probably predict right now that for the question 5, 10.3, so I'm going to go for furthermore 10.3, just not just 10.2. 10.2 is actually include only regulator. So if you look at 10.3, you basically repeat the 10.1 and 10.2 step right here. because I believe that they have a different setup of adding the three-phase shunt capacitor here in this situation. So the capacitor is nothing really complicated as what you can predict, because sun, as you know, is actually correct power factors. So this is actually, I didn't actually spend much time in chapter 9 to talk about this, but this is probably the only equation that you have to know to convert the shunt capacitance into the current. As I said before, you need current for the backward step. So when you go through all this step from 3, 2, 1, you have to sum out the current from the load, the current from the capacitor combined at the node 3, and then you add it up, bring it up all the way to node 1. So the only thing that for 10.3 different from the 10.2 is they are adding additional capacitors here, so it will affect the current at this node. So that's why you have to repeat the compute to compute the result for 10.1, 10.2. So this is the same thing that repeatedly over and over. And then add three-phase white delta connected distribution transformer. So the 10.4 is actually adding another one here, and the same thing will occur again. This is an initialization, and as you can tell, this is a distribution transformer rating and other information that you need in order to specifically model white delta connection. So if you have done the work of how to do the generalizations of this ABCD and capital AB matrices, then you probably will find out what is the ABCD and capital AB here from your initialization here as a whole. So this is basically per unit information you learned from junior years of power system. So I don't have to go through it more specific with you in detail. So that's the kind of information I think you will need for that model. So if you go through it the same way how you do it, this is conversion to line to neutral W, and then convert to delta current DI and D. Those are the required initialization for this distribution transformer. So as you can see that in terms of the while loop perspective, you're actually getting much more sophisticated for each step, right? So instead of having node 3 and node 2 for that line segment, now you're including regulator, you are including new capacitor, and then in this problem you are including an additional distribution transformer with a specific model. So you go through this specific statement. Again, this is hard-coded. You can see that this is a backward step, and this is a forward step. You will go through iteratively, and in the end you're going to check the errors here, which will be computed right here, and find out what are the necessary results before you the next step will be decided whether or not we will have to do this one more time or stop there. So yeah, this is another thing that from example 10.2, I have it in the MATLAB screen as well. So what I'm gonna do, I'm gonna provide you the MATLAB script for 10.1, 10.2, 10.3, 10.4 problem in the end of the chapter, as well as example 10.2 from the textbook. So those are the scripts that you can actually see and visualize how you do this computation. And I think it would be very helpful for you to go through the step and understand the backward step and forward step. As I said before, the main thing about this whole detailed powerful analysis is that you have to know the backward step, how you initialize, what are the things you need to initialize, and then the forward step, what are the things you need to do a correction, and what are the generalized matrices that you need for a specific two terminal elements. That's all you need. So when you are given a problem, let's say 3-node example during exam, you have to make sure that what are the generalized matrix you have, where are the nodes that you need to convert everything into the currents, and so on and so forth. So that's what I have for you guys for this chapter. If if you need any help or anything that relate to this MATLAB script, feel free to email me. I should be available in email. I will respond as soon as possible. So this time, because this is a little bit complicated situation, I'm going to put this MATLAB script in the M file so that you can have it and run it and experience yourself in the MATLAB environment, so that you can see how this computation go through by each iteration for each example. So I'm going to make this lecture short enough so that you will get some time to practice and check out with the script. And hope this helped. And see you on Wednesday class.